I actually, well, I'm recovering from a really bad stomach bug, but I decided that the show would go on. So, you know, and this is, I mean, I feel like, I can't walk much, but I can always talk. Okay, so, I basically over the past year worked on two different projects. One of them is maybe the first thing I ever did that has any danger of being useful to anyone. It's an application of hopefully very near-term quantum computers like the 70 qubit devices that Google is trying to build to generate cryptographically certified random bits. Hopefully I'll talk about that in some other venue this year when it's in a more mature state. Maybe today, this seminar, I want to tell you about the other thing I did, one that's not useful as far as I know, but I think it's a really cool connection though between two fields that were not at all previously known to be related to each other. And I'm really hoping that once I tell you about this connection, that some of you will be able to find other things that it's good for. Okay, so I'm going to tell you about some joint work with Guy Rothblum from the Weizmann Institute about a new connection between gentle measurements of quantum states and differential privacy. Okay, so first I'll have to explain each of those things individually and then tell you how they're connected to each other. And then, moreover, how we can actually exploit that connection and we can take known results from the world of differential privacy to actually design better quantum measurement procedures, or ones that were not previously known. Okay, I don't know any applications yet in the other direction, but using quantum to do something new in classical deep bit. But we can use this connection for something. Like most of my talks, I don't think you need to know you need to know very very little physics here. Because I know very little physics, but I'll just sort of quickly state some of the just the formalism that I'll use in this talk. So we'll be thinking about quantum states and measurements of quantum states. Okay, so the simplest kind of quantum state is called a pure state. It's a superposition. We represent it as a unit vector of complex numbers, like a quantum bit or a qubit could be alpha 0 plus beta 1, something like that. So it's we call it a superposition of 0 and 1 states. Or then once you look, then it makes up its mind if it wants to be 0 or 1. With probability, absolute value of alpha squared and absolute value of beta squared, respectively, if you ask it if it's 0 or 1. Okay, so these numbers alpha and beta are called amplitudes. They're complex numbers, and pretty much everything interesting about quantum mechanics boils down to the fact that these are not probabilities. These are complex numbers, and they are normalized in the 2 norm. Okay, so we'll just for the hell of it, because we can, we'll be dealing with the most general type of state in quantum mechanics, which is called a mixed state. Okay, a mixed state you can think of as just arising from an ordinary probability distribution over different quantum superpositions. Okay, so so in the most general situation, you may not know which superposition you have, but there's a mathematical object called a density matrix, okay, which is a common generalization of quantum pure states, quantum superposition states, and probability distributions, right? It includes both of them as special cases, okay? So these are d by d, if we're talking about d-dimensional systems, where measurements have d outcomes, these are d by d Hermitian matrices. By the way, classical probability distribution is the special case when the matrix is diagonal. Quantum superposition is the special case when the matrix is rank 1, okay? But if I had several different a distribution over several different superpositions, I could take a convex combination of different rank 1 matrices, and that would give me one of these density matrices, rho. The subtlety is that there can be completely different looking distributions over pure states that lead to exactly the same density matrix, right? Which is then telling you that those even though they look different, those are empirically indistinguishable situations, right? An example being an equal mixture of the 0 and 1 states is completely indistinguishable from an equal mixture of 0 plus 1 and 0 minus 1, right? They just you can calculate the density matrix. And in that case, it's just half the identity, right? It's just that 2 by 2 matrix. So that's this is called the maximally mixed state, by the way. Okay. So now given a state, we'll be thinking about measuring them. So for simplicity, let me just talk about 2 outcome measurements. A 2 outcome measurement can also be represented by a D by D Hermitian positive semi-definite matrix. I'll call it E. We don't. So the density matrix, its trace has to be 1, which captures the fact that I make a measurement, the probabilities of all the different outcomes have to add up to 1. For a measurement, we don't limit the trace, but we say each eigenvalue has to be between 0 and 1. Okay, and what you can do is you can apply this measurement to a state, and it either accepts or rejects. Okay, and the probability that E accepts rho is just trace of E times rho. Okay, so all I'm doing is I'm writing the standard rule for measurement in quantum mechanics, but in a slightly unusual form. Right, the squaring is built into the fact that we made these matrices and we took outer products and so on. So you have to do maybe a few lines to see that this is in the special case where this is a pure state, that this is just equivalent to the usual measurement rule of quantum mechanics. But this is how the experimentalist would often write quantum measurements. Okay, so but now something else happens when I make a measurement, other than I just see an answer, accept or reject. Okay, famously in quantum mechanics, the act of measurement changes my state, right? A similar thing happens even in the classical world with Bayesian conditioning, right? If I, condition on the result of measuring a system, then now I ascribe a new probability distribution to that system. Okay, but the difference is, in the classical case, the conditioning, in some sense, is just something that happens in my head, right? I could reverse it by the simple expedient of forgetting whatever I just learned, okay? In the quantum case, the change to the state is something objective that happens, which, someone else measuring the same state could also see that it had been damaged, okay? And let me just give you an intuition for, okay, so famously, right, if I take like a particle, which is, let's say an electron in a superposition of many different positions, and I measure its position, then I force it to, down to a single position. I localize it, right? And that's a very drastic change to its state. Okay, but not all measurements in quantum mechanics on all states are so destructive, right? I mean, I read a book, I can read the same book again, okay? Or I take a qubit that's already 0, I measure to see if it's 0 or 1, it tells me it's 0, okay, good, my state hasn't been damaged at all, right? So the general rule is that if given knowledge of the state, you could almost perfectly predict the outcome of a measurement on that state, then the measurement can be implemented in a way where it is not very destructive. Okay, where after you implement it, you can get back almost the same state. And you can see why just from like looking at this picture, right? If like, if the outcome is almost perfectly predictable, that intuitively that says our state is sort of already really close to one of our basis vectors. And then what usually happens is just that it snaps to that basis vector. occasionally it does something else, but usually it just snaps there, and so there's only a small change. Okay, but if I measure a state like this, well then, I've given the state no choice but to, be drastically changed no matter what the outcome of the measurement. Okay, so that's a much more destructive measurement. It's one that sort of took place in the wrong basis, if you like. Okay, so yeah.
Can I just ask
Yeah.
back earlier?
Yeah.
So if you, with a measurement matrix,
Uh-huh.
like what happens if you multiply it by half? So this, like,
You can
I
do
thought you
that-
measured
yeah.
with respect to a basis, but
Yeah. Okay.
this,
So good. So this is actually, this is the most general formalism, which also includes measurements, where the basis could also involve some ancilla qubits, right? So this automatically takes account of it, and we're only looking at the effect that it has on our system that we care about, right?
Oh, okay.
So there are some general measurements involving ancilla qubits that can't be written as just a measurement on on your little system. You need to measure a larger system, and then this captures even that. Okay, but if in the special case where the measurements were just a basis, a d-dimensional basis, then each of these would just be rank 1 matrices, corresponding to each of the basis vectors. All right, great. So okay, a gentle measurement is important in many places in physics. It's been a major ingredient in a lot of the things that I've been interested in doing, which have involved manipulating things like quantum advice states or quantum money, which could be better than Bitcoin someday because it would remove the need for a blockchain, or quantum copy protected software. I don't know if that's good for the world, but it might be possible. So I've been interested in, taking these states and, reusing them over and over, making a long sequence of measurements without damaging them. And when you do that, you have to be very careful to only measure them in the right bases, right? And, in a way that doesn't destroy them. Okay, one trick that can very often be used to help you achieve that is, what we in TCS know as amplification, right? You can always, if you have a bunch of copies of your state, then you can often make a measurement, on all the copies together, which would be much less destructive than just measuring any one of the copies individually, right? And with sometimes the probability of damage just going down by exponentially with Chernoff bound type of behavior. Okay, so the starting point for the new work that I want to tell you about is that I had a paper in Stock this summer, which was about a task that I called shadow tomography. I had a boring name for it, but this name was suggested by a physicist. They're always better at naming things. So basically, a few years ago, I had asked the question, so quantum state tomography means, you have some number of copies of a quantum state, and, you would like to learn the state, which means learn its density matrix, at least approximately, by somehow measuring those copies, right? And so, this is a very, very common situation in experimental physics. And so we could ask the question, well, how many copies of the state are necessary and sufficient to, to learn it, to do tomography, right? So, surprisingly, for such a basic question, it was only a couple years ago that question was fully answered. Okay, and so there's work, papers in Stock a couple years ago by Ryan O'Donnell and John Wright, and another one by Ha et al. Okay, Ha et al. Are physicists. O'Donnell. Let this be an inspiration to all of you of just how little physics you need to know to make big contributions in quantum information. Okay, but so they, so what they have shown now is that order d squared copies of rho are necessary and sufficient to do tomography up to some fixed accuracy. Okay, which intuitively it's kind of what you would expect, right? Because it's a d by d matrix. It's got d squared parameters. each state you measure, you feel like it gives you a little bit more, and you feel like you should need d squared. But actually proving this involved all this representation theory and super interesting stuff. Okay, so but now I want to consider a different setting. Suppose that we don't need to learn rho necessarily as a quantum state. Okay, we only need to learn how does rho behave on a list of known measurements. Okay, so if we we don't need to do full tomography, we just need to learn the shadow that rho casts on some known list of measurements. Call them E1 up to EM. Okay, so for example, these might be all the measurements that can be applied by quantum circuits with at most n squared gates or something, n being the number of qubits, right? That would be a good example, right? All the efficient measurements, or so we have some restricted set of yes or no measurements where all we want is to learn the behavior of rho approximately on each of them. Okay, so you want to know trace of EI rho to within some additive error of epsilon, and you want to know that for every I, so with high probability, high success probability. Okay, so how many copies of rho do you need to do that? Well, certainly d squared suffices. You could just learn rho, do tomography, do their thing, and then you get whatever you want. But there's also at a completely different extreme of parameters. There's something else that would work. Can anyone suggest it? It's not something subtle. How could we do it with about m copies? Oh, just measure. Yeah.
Yeah, we can just run each measurement.
Yep.
Different measurements on each copy.
Yeah, exactly. Thank you, William. Yes, we can just measure each, apply each EI to separate copies of rho, right? And that would also work, and that would give us, something like m copies suffices. Okay. Now the question that I posed actually at a Barbados workshop a few years ago was, well, could you what if d and m are both exponentially large? Okay. You want to know behavior of an n qubit state, so that's 2 to the n dimensions, right? D is 2 to the n, and you want to know its behavior on all, circuits of size n squared, right? So m is, exp of n squared, okay? Could you still do it with a polynomial number of copies of rho? So, what we're asking is, is shadow tomography possible with a number of copies that is polylogarithmic in both d and m? Okay, and so what I showed is that the answer is yes. I had actually tried to rule this out. I couldn't do it. Now I know why I couldn't rule it out. So the bound that I get is that it is possible to do this. I design a protocol that does it using a number of copies of rho that's like log of m to the 4th times log of d divided by epsilon to the 4th. And I'm almost certain that this is not tight. Come on, right? Actually, I don't know if the bound needs to have any dependence on d, right? The only lower bound that I know is that log m over epsilon squared is necessary, and that's even in the special case of classical probability distributions that much is necessary. So so there's still a gap here. But the protocol, I'm not going to have time to show you all the details of this protocol, but it's somewhat weird. It involves taking your whole list of measurements, E1 up to EM, looking at it as a batch, and then the basic idea is that there's this very small subset of these measurements that are very influential. Right, where if you knew its behavior if you knew rho's behavior on those measurements, then you could sort of deduce its behavior on all the others. And so the problem reduces to figuring out what are these influential measurements. For those of you who know the multiplicative weights update method, what I'm doing is basically an instance of that. It's also very related to boosting in machine learning. The way that you show that there is this small set of influential measurements is basically multiplicative weights. Okay, but then there's kind of a second big problem, which is I have to figure out which measurements are my super influential ones, No one is telling me. So then I have to repeatedly go through the entire list of measurements and try to search for an influential one, but do it without damaging my states too much. And I only have polylogarithmic, number of copies of the states. And so then that is where we have to use ideas from gentle measurement, and we have to be super careful in how we measure. We use a result called the quantum Orr bound, which I had claimed to prove in 2006. Turns out that my proof was wrong, but fortunately in SOTA 2017, Aram Harrow and Ashley Montanaro and Cedric Lin very kindly, not only did they find the error, they also gave a correct proof. Okay, so now we can use that. Okay, so so what happened was that I gave a talk at Weitzman about these shadow tomography and the importance of gentle measurement, and then Guy was in the audience, and he said, well, wait a minute, this sounds a lot like differential privacy, and I said, what? First of all, I barely even know what that is. Okay, but secondly, anyone can, everyone always thinks that whatever is being talked about is related to their own hobby horse. Right? You can connect anything to anything, right? I was very skeptical. Okay, but here is what Guy pointed out to me. Is there another board here? No. Okay.
Might be board in the back.
Oh, really? Is this a board? Looks like a board. Yep. All right, good. Hopefully I won't be writing on the wall. All right, let me let's see. All right, let me just define gentleness and also define DP. Okay, so and then we can see why Guy thought that there might be a connection. So we're going to say that a measurement M is alpha gentle when let me just say alpha gentle. Sorry. And what we mean here is on product states. Okay, so if for all states rho, which can be written as just a product of n unentangled states, rho 1 up to rho n. Okay, well we'll see later why we want to impose this condition that the states are not entangled. But just imagine that I have a bunch of separate quantum states, like n of them. So for all these states, and for all possible outcomes y of applying the measurement m to this collection of n states, after applying the measurement and conditioned on getting the outcome y, we can recover a state that is very close to our original state rho. Okay, so here this is trace distance. This is just the standard distance metric between quantum states. It's a generalization of classical variation distance, right? And it basically just says you look at the sum of the absolute values of the eigenvalues of this difference. Okay, so so it says for every product state and every outcome, getting that condition on getting that outcome does not change the state by much. Okay, so what is an example? Let me give you an example of a measurement that is gentle. This is an example that's actually known to the experimental physicists, right? They sort of so let's say that I have a collection of qubits. So I have n qubits. Like that, and let's say that I would like to do a measurement that tells me the total Hamming weight. Okay, I just want to know how many qubits are in the state 1. All right. Well, if I just do that naively, then that's going to be very destructive. It will not be gentle at all. Okay. Why not? Well, because I can look at the what is the distribution over possible Hamming weights, and it looks like what, anyone? It's a Gaussian, right? It's a sum of independent random variables. If you don't know what a Gaussian looks like, it's kind of like that, okay? And physicists would call this a wave packet, okay? But then when I measure, the outcome of the measurement is one specific Hamming weight, like maybe this one. So I localize the wave packet, right? I force the whole thing down to one particular Hamming weight. Okay, so that's very destructive. Okay, but you could learn about the Hamming weight in a much less destructive way, and a good way to do that would be to just make a measurement that tells you only the Hamming weight plus some random noise. Okay, let's say I make a measurement that tells me only the Hamming weight plus some noise of average magnitude, about more than square root of n. Let's say. Okay, and so sort of the noise should be larger than the width of this wave packet. Okay, and this there are standard ways to implement that by these measurements like this. Okay, but what does that do? Well, that says if I know the state, right, then I pretty much know, I more or less know the distribution over possible measurement outcomes, right? It's something, it's some, let's say, a distribution that's sort of, more or less centered around the correct set of Hamming weights, right? So I learned something about the Hamming weight, but this is much less destructive. And in fact, I could, so what kind of noise? One thing I could do is Laplacian noise, which means like the probability that the noise term will be equal to k will be like e, something like e to the minus epsilon times the absolute value of k. Okay? So this is, and this will be a good choice. Okay. Now the physicists actually use this. For example, if they have a collection of photons and they want to measure, they want to know the total polarization, right, or the average polarization. Okay, they know that if you make the measurement with a lot of noise in it, then this is not destructive to the photons. Okay, not too destructive for exactly this reason.
So you didn't mean k over root n or something?
Well, okay, I said, so I guess that's in the choice of epsilon here.
Oh, okay, so epsilon, we think of epsilon as 1 over root n.
Yeah, exactly. Thanks, David. Mm-hmm. Okay, so I mentioned there's this technique. Okay, now let's talk about the totally unrelated subject of differential privacy. Okay, so first of all, what is differential privacy? It's an area of CS, that's seen a lot of growth over the last 12 years. And I never really paid much attention because I said, what do I care about privacy, right? I just put everything on my blog, right? So it just didn't seem, it just didn't seem fundamental. Okay, I was completely wrong. It is fundamental. I'll show you why. It's an area where you imagine that you have some huge database of sensitive records, like people's medical histories or something. And you want to let people make queries to learn useful aggregate features of all this data. How many people have cancer or whatever. But you want a mathematical guarantee that no one is going to be able to use the query results to learn too much about any individual user. Okay, so. So you have to, it's like a philosophical question. Well, what do you mean by that? Okay, but there's a proposal, and this, these tools are actually now used apparently by both Apple and Google. Although I just read an article that said that Apple implemented differential privacy, but it set the parameters to be so weak that it doesn't actually, give you any real privacy. You know, it's like they've handcuffed themselves, but the handcuffs are made of tissue paper. That's what Frank McSherry said. But so I don't know the details of supposedly Google has done it a bit better. Okay, but so what is the definition of privacy that people settled on? Okay, so we'll consider like a randomized algorithm A, querying a database of n records, like that. And we're going to say that A is epsilon differentially private, EPSDP, if for all pairs of databases, X and X prime, that differ in only one entry. So they differ on only a single xi. And for all possible outputs y of A, the probability that A, given x, outputs y is at most 1 plus epsilon times the probability that A, given x prime, outputs y. Okay, so this is the definition. You might wonder, why do we need this multiplicative? So it's like any one person changing their data or dropping out of the database has at most a small multiplicative effect on the probability of any outcome of your query. Okay, this seems like a strong definition. You might ask, do we really need this multiplicative guarantee? Wouldn't an additive guarantee be good enough? Then you're sort of vulnerable to the following type of thing. If it were additive, you would have to say that the following algorithm is privacy preserving. Just pick one person at random from your database and reveal all their data. Probably that person won't be you, right? Won't be any given person. So it's a good additive. You get a good additive guarantee, okay? But sort of clearly that sucks, right? So the multiplicative guarantee, among other benefits, it rules out stuff like that, okay? So what is an example? Let me try switching pens. What's an example of a differentially private algorithm? Well, let's say that we're trying to query something sensitive. How many users in our data set are left-handed necrophiliacs? Or I guess the left-handed part people would be fine with it being known. Right? I'm left-handed. Okay, but whatever. How many have cancer? Whatever. If I just reveal the number of people, right, then that seems really bad, okay? Because if I see that the number Bob has just joined the database at the same time the number of left-handed necrophiliacs was incremented by 1. All right, we have a problem, okay? But if I just reveal the number with some noise added, right? For example, this noise following a Laplace distribution like this one. Okay, then I have the following sort of guarantee. So Laplace noise looks like this, and so now if the number of necrophiliacs changes by 1, then this distribution changes to this distribution. Okay, but you notice that for each possible output, for each possible number that could be returned by our algorithm, these two numbers are kind of multiplicatively close. Right? In fact, they differ by about only a factor of 1 plus or minus epsilon. Okay, so Guy said, isn't it a coincidence that we use the same kind of tools, like adding noise to get gentleness and also to get differential privacy, right? So the main result that we prove in this new work is that this is not a coincidence at all. Okay, let me just first upgrade this definition to a quantum definition, right? Yeah.
So on the specificness of the Laplacian,
Yes.
I think in the differential privacy world, it's convenient because of the way it composes, right?
Yeah.
But there's nothing else that's special about. You could add Gaussian noise.
So you could, except with Gaussian you run into trouble because at the very far tails you lose your multiplicative guarantee that you want.
I see.
That's the problem with Gaussian, right? So there is a generalized definition called epsilon delta differential privacy, where you allow a tiny additive error, and Gaussian noise could satisfy epsilon delta dp. But if you want to satisfy the stricter definition, then you need Laplace noise.
And for the quantum problem too, is there a special Laplacian provision?
Well, it's again, it's because I had this strong definition that said for every possible outcome, right? That's one answer as to why we really want Laplace noise here, right? Like, we could use Gaussian noise, but then I would have had to relax this definition. Okay. That's a good question. Okay, so let me, so suppose we want to protect the privacy rights of quantum states. We do that. So let's just say that, a quantum measurement procedure, M, is, which is querying, I'm just going to, change the letters. Everything else will be the same. Querying a product of n quantum states, rho 1 up to rho n, is epsilon dp if for all rho and rho prime that differ in only one entry, and for all possible outputs y, probability that m rho equals y is at most 1 plus epsilon times probability that m on rho prime equals y. Okay, so let's take that as our definition of quantum differential privacy. Yeah.
One entry.
Yeah, meaning one state. Only like one rho survives. Okay. So, all right, let me put it here. Okay, so let me tell you our main result. Okay, it's that there is a connection between these two concepts, but goes in both directions. Okay, one direction, it's like very strong. Any measurement that is alpha gentle is also O of alpha differentially private. Okay, and this is actually just a few lines to prove once you know to ask the question. Okay, now the second part is to go from differential privacy to gentleness. That is harder, and there's a lot more fine print. But this is maybe the more the direction that we're actually able to use and get something from. So so let me suppose that M has a special form, that it just consists of a classical DP algorithm applied to results of measuring rho 1 up to rho n separately. Okay, so one of our main open problems is whether this restriction can be removed. Right? It sounds like a strong restriction, but actually this is already enough to encompass pretty much any of the examples that we care about in practice of quantum DP algorithms. Okay, they all seem to look like that. We can show that there are quantum DP algorithms which do not have this form,
which do not arise from just taking a classical DP algorithm and applying it to outcomes of quantum measurements. But so far we haven't found any use for them. Okay, so let me assume this. Then it is possible to implement M in a way that's O of epsilon times square root of n gentle. Okay, so you'll notice we lose a factor of square root of n here, right? Isn't that a lot? Well, so this part 2 is really interesting. It's interesting mainly in the regime where epsilon is somewhere between 1 over n and 1 over square root of n. Okay, so then I should point out that if epsilon is less than 1 over n, then being epsilon differentially private just means that you barely look at the database at all. Right? Because you could flip every single entry and the output still wouldn't change much, right? So that's kind of degenerate, okay? But there is this regime where epsilon is less than 1 over root n, and there this theorem does give you something interesting, right? Now we can actually show that this factor of square root of n is tight. It is necessary here. And we can also show that the restriction to product states was necessary for getting an interesting theorem of this type. Okay, maybe it's worth saying something about that. You might say, why couldn't I allow all n of the states to be entangled? Well, I could, but it turns out that if you do that, then the best that you can get is that anything that is epsilon, this part goes through just fine. For this part, all you would get is that anything that is epsilon differentially private is most O of epsilon times n gentle. Okay, and so then that's only interesting when epsilon is less than 1 over n, right? Which means your algorithm is the trivial algorithm, right? So that's the issue with entangled states. And if you're wondering, what causes the issue with entangled states, well, just consider a case like this. Okay, this is Schrodinger's cat. Okay, it's n qubits that could either all be 0 or all be 1, right? And imagine that I want to measure the Hamming weight, plus some noise term which is less than order n, right? So then that will be a perfectly good differentially private algorithm, right? It satisfies the definition of DP, but it's not very gentle at all. Because no matter how much noise I add, as long as the noise is less than n, it still tells me whether I'm in this component or this component. And therefore it collapses the state. It damages it by a lot. Okay? When I have an unentangled state, intuitively, I get this law of large numbers behavior, right? I get this sort of concentration to a Gaussian, which is what I can exploit here. Okay? So, another interesting comment. So if you worry about computation, this direction, is just completely straightforward, computationally efficient. The direction 2, as far as I know, might not always be computationally efficient. Okay, so it's an information theoretic result, and and if I had a polynomial time DP algorithm, and I wanted to get a polynomial time gentle measurement, well, I can do that as long as the output of my DP algorithm can be efficiently what is called Q-sampled. Okay, this was a term defined by Dorita Haranov and Amnon Tashma, and it basically just means if let's say these different i's are the different possible outputs of my DP algorithm, on a given database X, or a given state row, then I have to not only have an efficient algorithm to sample I with probability rho sub I also need an efficient algorithm to create this state, right? Superposition over all I, square root of PII, right? So that's a stronger requirement, right? If I measure this, then I get a sample from the distribution I want, but the ability to prepare the state could be stronger. Because I need it to not be entangled with any other garbage register, okay? And in fact, Aharonov and Tashma made the observation that if everything that could be efficiently Q-sampled could be efficiently, if everything that could be efficiently sampled could be efficiently Q-sampled, then, for example, you would get a polytime quantum algorithm for graph isomorphism, right? In fact, for all problems in SCK, including breaking lattice-based cryptography. Okay, so, I had in 2002 this quantum lower bound for finding collisions, which says that there, in the black box setting, there are things that can be efficiently sampled but not Q-sampled. Okay, so so I don't know of any real-world case where this is actually an issue, but but it could be in principle. Okay, so. All right, so I'll tell you what I think I'll do is, yeah. So let me just make some more comments, and then about the application, and then I'll just stop, and then if everyone's welcome to leave, and then if anyone wants to hear something about how you prove these things, I can say that. Okay. All right. So so you might wonder conceptually, why should we expect differential privacy to be related to gentleness? Well, actually, there was a forerunner of this connection in some really beautiful papers from 2014 or so by Cynthia Dwork et al. Okay, Dwork was one of the originators of differential privacy, and what they did in these papers is that they made a connection between differential privacy and what they called adaptive data analysis. Okay, so basically, scientists may want to, do many studies, reusing the same data set, right? Because this is, you go to war with the data you have or whatever, right? And you may think that, okay, as long as, each study that I do has a good statistical power, then I should be fine, right? I should be able to just keep reusing the same data, but actually it's not fine, right? It's a problem because, the very questions that I'm choosing to ask in my next study might depend on the results of the previous study, right? So, so it's not as if I'm coming to the data fresh, right? I might have asked questions that I wouldn't have asked if not for some peculiarity of this particular data set, right? And then that, that ruins the sort of statistical validity of my scientific experiments. There's a paper called The Garden of Forking Paths that argues that many social psychology studies have been subject to this problem, okay? But now, so then these people ask the question, well, is there a way that we could keep querying the same data set over and over that would be safe? And they observed that you can do that as long as the queries you make are differentially private, okay? And intuitively, it's because of sort of a classical version of what we're saying, right? That, anything that's differentially private is sort of only damaging the data by a little. Okay, but here damaging means in the Bayesian sense, the sense of Bayesian updating, right? Where you could undo the damage by just forgetting, what you learned, or, retracting your study, or, forgetting it ever happened, right? Whereas in the quantum case, when we talk about gentleness, we're talking about actual physical damage to the state. Okay, but otherwise, the two connections are actually very similar to each other. All right. Yeah.
So I had one question.
Yeah.
I know very little about differential privacy, but I kind of remember that there's sort of two regimes. One is like where there's some data set, and then you get to ask a question, gives a noisy answer, but it's stateful, like remembers what you've already asked, and then if you ask it, it's signed. more and more, and another one is where you just publish it online,
Yeah.
and that's that. Does it relate to one more than the other?
So I'm not assuming a stateful algorithm here, right? The algorithm, the DP algorithm, right? Just each time you make a query, it just goes, it goes to your database. Well, it goes to your database. Except in the quantum case, right? These are quantum states, and they do change as a result of the queries that you
So
make.
in
Necessarily so.
In the just pure DP thing,
Mhm.
I mean, if you made the same query many times,
Yep.
you could learn.
Oh yeah. So DP, right? There's always a limit to how many queries you can make. Right,
Okay.
maybe that's worth saying, right? But I mean, like if I just kept making queries over and over, eventually I can learn that Bob's a necrophiliac, right? I mean, eventually, right? Eventually I'll lose, because what's good about the definition is that the loss in the privacy parameter is only additive, right? Like, if I make, queries that have the DP parameter epsilon1, epsilon2, and so forth, then the total differential privacy will be at worst the sum of the epsilons for the individual queries. And in fact, it's even better than that. There's something called advanced composition that says you get to take like a square root, right? And it only grows like the square root. Okay, but it can grow like that in their example.
Yeah, there are just some negative results in differential privacy from crypto, and I was
Oh
curious
yes.
to percolate, but
In
I don't quite
fact,
understand.
we were able to use one of those negative results in order to derive a negative result about shadow tomography.
Yeah, that's what was it?
Yeah.
The
In
trade
fact,
tracing one?
yeah. About the negative result was based on these trader tracing schemes. Yes.
Okay, okay.
Yeah. So I mean, I didn't know all this stuff, but Guy knows all this stuff. Okay. And so, all right. But let me just. I'm getting too far ahead of myself. So let me just. Tell you what is the application to shadow tomography here, right? Or what's the, what were we able to exploit this connection for? All right, well, so we can show that it is possible to do shadow tomography using this number of copies of rho, using K, which is O tilde of log squared M times log D divided by epsilon to the 6. Okay, again, M is the number of measurements, D is the dimension of your Hilbert space. Okay, so the main advantage in this bound is just that the 4 has been reduced to a 2. Okay, we know that 1 is necessary. This log D is still around. I don't know if we can get rid of that. Epsilon to the -4 has become epsilon to the -6. That's a little worse, but we're working on that. All right, but actually more interesting than the improvement to the bound is some additional features that we get from this new shadow tomography algorithm. Okay, and one of them is that this algorithm is online, which means the EIs can just be given to you one at a time. And then for each one, you immediately respond with the approximate value of trace EI rho, without needing to see all the future EIs, right? So it's a completely online procedure, which is something that I guess I hadn't really dared to hope for. Okay. Also, this procedure is itself gentle. Okay, which means you can apply the entire shadow tomography procedure. And afterward, you have almost the same states, rho sub k that you started with, or so rho tensor k that you started with, and they can then be used for something else. Okay, so and I guess it's also differentially private, but that's no great surprise. Okay, so how do we do this? Well, we take a known result from classical differential privacy, which is called the private multiplicative weights, or PMW algorithm. And it's due to Moritz Hart and Rothblum, 2010. Somehow Guy had heard of this, and so we sort of upgrade it to a quantum algorithm, quantum PMW. Okay, and then we basically just we show that this algorithm, and what it is it's an algorithm for answering a large sequence of queries in an overall differentially private way. It had the novel feature of being online. It used multiplicative weights, so pretty kind of reminiscent of what I did for shadow tomography, and then so we use the fact that this algorithm is DP and we use our equivalence theorem in order to derive that this algorithm is also gentle at each step, right? And so it's answering each query while only damaging your states by a little, and so you can keep going. You can keep apply each EI in sequence. And so that's basically what we do there. So let me I'll just mention some open problems, and then if anyone really wants to stay and question me about how these things are proved, I can tell you something about the proofs. Okay, so the open problems.